today we're going to look more about probability and talk about something called the addition rule. So mainly in this section, we're talking a lot about or statements as well. I know we've seen some and statements, and we'll look at that still here too, but we're going to really focus about or statements. So one event or another event. All right, so first, two events, A and B, are mutually exclusive when A and B cannot occur at the same time. Now, I do want to note that mutually exclusive and the idea of independent are different concepts. So events are independent if one does not affect the probability of another one. This is about things occurring. So events are mutually exclusive if A and B cannot occur at the same time. So again, these are two different ideas. You just want to be careful not to mix them up. So for instance, for mutually exclusive, A and B have no outcomes in common. When two events are mutually exclusive, they have no outcomes in common. And so what happens is P of A and B is 0. So there's no overlap between those two events. If we're doing a Venn diagram, okay, and let's say this was our sample space. So here's event A. And here's event B. And what we see here is when the events look like this, so there's no overlapping region, then these are mutually exclusive. So they have nothing in common. When there is an overlapping region, right? So right here, P of A and B, so this is not 0, right? There's something in between there that's overlapping, then these are not mutually exclusive. So let's look at a few examples. Okay, so we're going to decide if the events are mutually exclusive or if they're not mutually exclusive. So the first one, let's say we're talking about rolling a die here. So event A is that you roll a 3, and event B is that you roll a 4. Now think about it. Can you roll a 3 and have that 3 also be a 4? No, it doesn't make sense, right? So 3 and 4 are two totally different numbers. They're two totally separate events and outcomes. So there's no overlap here between rolling a 3 and rolling a 4. So these events are mutually exclusive. Now for the second one, let's say you have event A is randomly selecting a male student, and event B is randomly selecting a nursing major. So think about it. Do these events overlap at all? Well, yes, they could, right? Because you could have a nursing major who is also a male student. So you could have a person here that fits into both events or both categories. So because it's possible to have overlap, these are not mutually exclusive, right? Because you could have a male nursing student. Event A, randomly selecting a blood donor with type O blood and randomly selecting a female blood donor. So again, could one person, because we're talking about people here, occur in both events? Yes, they could, right? You could have a female who is also type O. So because you have overlap between these events, they are not mutually exclusive. Right? Because you could have a female who is type O, right? So it's possible to have overlap in those events, so they are not mutually exclusive. The addition rule. So in this section, we focus on probabilities, like I mentioned already, containing the word or the idea of or. So I say the idea because sometimes we don't always use the word or, although we do most of the time, but it could also be the idea of one event or the other event occurring. So when we say something like P of A or B, so the probability of A or B, this means that event A can occur and B does not occur. Event B can occur and A does not occur, or both events occur, right? So as long as one or the other occurs, then we're counting that as a sort of like a win, right? So event A could occur, event B could occur, or both can occur. As long as one of those is occurring, then it counts. So this probability actually is affected though based on if the events are mutually exclusive or not. So the general formula for calculating an OR probability is that we add up the probabilities of each individual event and we subtract the overlapping region if there is one. So if there is an overlapping or intersecting region like this here, what we do is we take the probability of A, we take the probability of B, and then we subtract out the probability of this overlapping region occurring. And the reason we do that is because when we find the probability of A and we find the probability of B, we've actually counted that overlapping region twice, right? Because it gets counted once for A and it gets counted once for B. So we have to subtract out one of those overlapping regions so we don't double count. That's why we do the subtraction. Because you've already counted it in A and you've counted it in B. You've counted that overlapping region twice instead of just once. So we have to subtract it out. Now, if your events are mutually exclusive, if they look like this, then we don't have to worry about that because there is no overlapping region. It's just 0. So we can just add up the two individual probabilities. And that's what this rule says here. And this can be extended to any number of mutually exclusive events. So if you have a whole bunch of events that are mutually exclusive, then you can just add up those probabilities for an OR statement. All right, so let's try it. So we're going to do 2 examples here. So let's start with example 1. So you select a card from a standard deck of 52 cards. We're going to find the probability that the card is a 4 or an ace. So we can separate our events here. So right, let's say event A is pulling or selecting a 4, and event B is pulling or selecting an ace. Right. So if you think about these events, these are totally mutually exclusive, right? A 4 and an ace are not the same idea. It's not possible for both of them to be on the same card, right? So if I pull one card, I can't get a 4 and an ace at the same time. So there's no overlapping region there. These are mutually exclusive. So the probability of getting a 4 or getting an ace, and sometimes we do is we'll even just, instead of labeling our events, we may just say something like probability of 4 or ace, like that. Oops. Sometimes it just helps us mentally just to write out what we're talking about. It's just going to be the probability of pulling a 4 plus the probability of pulling an ace, right? Because it's mutually exclusive, I don't have to worry about any overlapping region or double counting. So I just add these 2 probabilities together. Now, in a deck of cards, there are 4 4s, 1 for each suit. So 4 out of 52. And for an ace, you have a chance of getting 4 out of 52 here. So what happens when I add these together, I have common denominators, I get 8 out of 52. And now I can go ahead and use my calculator and I get about 0.154. So that's our probability here of getting a 4 or an ace. Now, remember, we're not subtracting the 2, we're not taking out one card and then pulling a second card here. So this is not, we get a 4 and then we get an ace. We're just looking for one card, which is why your denominator remains 52, right? Because basically there's 8 chances altogether. There's 4 4s, there's 4 aces. So I have 8 opportunities to pull the card that I'm looking for out of 52 altogether. And so the biggest thing with probabilities is really just thinking about what the question is asking. We've seen a lot of different wording, right? Are you pulling a 4 first and then an ace second? Do you have an and idea? Here we have an or idea. So it's a 4 or an ace. There are 8 options for those cards out of the 52. So let's do the next one. You roll a die, and we want to find the probability of rolling a number less than 3 or rolling an odd number. So event A could be here, roll a number less than 3, and event B could be roll an odd number. So the probability of A or B, again, we're not rolling the die twice here. We're just rolling it one time. And we want to see what our chances of getting one of these things to happen. Well, for numbers less than 3, you have only 1 and 2 there. So there are 2 options out of the 6 to get that number less than 3, right? You can either roll a 1 or you can roll a 2. That's the probability of A. Now I can also add in the probability of B, right? Because it's an or statement. And I want to roll an odd number. Well, think about my options. My options here could be a 1, a 3, or a 5. So I have 3 chances there to roll an odd number. But these events are not mutually exclusive, and we can actually see it right here, right? You can see that I had that same number occurring in both events. So these events are not mutually exclusive. So what we have to do is subtract out that intersection there, that A and B statement. And I can see that it happens one time, right? There's one number that overlaps in those 2 regions. So I have 1 out of 6 that I subtract. So I have 5 over 6 minus 1 over 6, which is 4 over 6, and or 2/3, so about 0.667. Okay, so things that are mutually exclusive, much simpler. If they're not mutually exclusive, you have to look at that overlapping region, right? So subtracting out that and piece. Because I have one number that overlaps here, I need to go ahead and subtract it out because I've counted it too many times. That's the reason. And now look at your answer, right? Before I simplified it, it was 4 out of 6. Look at the 4 different numbers for our events. You had the number 1, the number 2. I've already done number 1, I don't need to count it again, the number 3, and the number 5. So you can see you have 4 different ways to get that die to roll the way you want it to. So really that's where that 4 comes from, right? So when we subtract, we're not changing the probability or doing anything incorrectly. We're taking out that region that gets double counted, right? Because we're counting that 1 twice here. We're counting it here and we're counting it here. So I have to subtract one of them away so that I'm not double counting. And that's what that subtraction piece does. All right, let's do another example here. I'm just getting my notes out so I have them all with me. Okay, so finding the probabilities of mutually exclusive events. So the frequency distribution shows volume of sales in dollars and the number of months in which a sales representative reached each sales level during the past 3 years. Using this sales pattern, find the probability that the sales representative will sell between $75,000 and $124,999 next month. So if I look at my table here, I can see that I'm actually looking at these 2 groups, right? Now, whenever you have a frequency table or frequency distribution, this should be mutually exclusive automatically because the way you have set it up is that your classes do not overlap. We really stressed that right back in chapter 2, that when we have a frequency table, our classes should never overlap. So because we don't have any overlapping classes here, we're not double counting anything, right? So the number 7 is only for numbers between these 2 values. The number 9 is only for numbers between these 2 values, and these 2 classes don't overlap. So I have mutually exclusive events here. So to find the probability then, I'm looking for the probability of actually getting between 75,000 and 99,999 plus the probability between 100,000 and 124,999. So this is an or event here, right? Because we could do this one or we could do that one. We want to combine them together. So how many months do I have altogether? If I go ahead and add these up, I do see I have 36 months. Okay, so adding up my months. So the chance of getting the first category, it would be 7 out of 36. And the chance of getting the second category is 9 out of 36. And I want to find the probability that the representative will sell somewhere between those two categories. So what's the chance that he's going to hit either one of those categories? So I have this or idea here. Even though I didn't say the word or, we're saying it's okay to be in this category or this category. So we're going to add these together. And when I use my calculator, I get about 0.444.